Let us start this lecture 8 as usual with a thought process from W. F. Hilton, who made this statement in 1951, who happens to be a scientist in NASA. He says that the whole problem of aerodynamics, both subsonic and supersonic, may be summed up in one sentence. Aerodynamics is the science of slowing down of air without loss after it has once accelerated by any device such as wing or a wind tunnel. But I would suggest that whether a wing, flow over a wing or a flow through the propulsive devices. And it is thus good aerodynamic practice to avoid accelerating the air more than is necessary. It is a very important statement. That means, we should not really accelerate the flow to the extent what is not required, and that is the basic thing what we will be doing while designing a propulsive device. And so, also analyzing, we need to look at compressible flow. And I had already initiated discussion in the last lecture on the compressible flow. And if you recall, I asked a question whether a fluid will be compressible or a flow will be compressible. Then we define a term known as compressibility factor. We are using a symbol K, but there might be some other symbol for compressibility factor. And also I told you that it will be change in density divided by the change in pressure. In other words, change in density per change in the pressure per unit density, that we call it as a compressibility factor. And we also talked about there are other definition as well, because this is a more general, but to be more specific, right, one has to talk about the compressibility factor for isothermal flow condition or for an isentropic flow. And considering the flow to be isentropic, then we use those definition to derive equation for what? For speed of sound. And I also try to give an idea about what is the sound, how it behaves, what are the mechanism of the sound propagation, going to the microscopic effects or the molecular level. As I told you yesterday, that by using the kinetic theory of gases, one can derive an expression for average molecular velocity, which is equal to root over 8 pi t divided by root over 8 pi r t divided by k, or some constant, right, and which can be related to the speed of sound. And if you look at the speed of sound, we have derived for an ideal gas, right, that is equal to root over gamma r t. If you look at this root over gamma r t, that means it is a function of the temperature and also the fluid properties. You remember I had taken example of air and helium. I saw that at same temperature it is having different speed of sound. And keep in mind that R, what I am using that equation or expression, is basically specific gas constant, which is ratio of universal gas constant and molecular weight. When I talk about molecular weight, then molecular weight of particular gas. And this speed of sound will be different in different material. For example, solid, for example, water, right. Will it be different or it will be same? It will be actually different, because it depends on the properties of the fluid. And based on this speed of sound, which is very essential to delineate whether the flow is compressible or incompressible, we define a term known as Mach number, which is a ratio of velocity and speed of sound. And based on this Mach number, we can divide the flow into various regimes. And what are those regimes? One is, of course, you can call it as a subsonic flow when Mach number is less than equal to 1, because Mach number equal to 1, we call it as a basically what you call, we call it as a sonic flow, right. And when it is less than 1, we are supposed to say it is a subsonic flow. When it is greater than 1, we should say it is supersonic flow, as usual, right. One is subsonic, other is sonic, other is supersonic. However, people like a person Theodor Wankerman, right, you know him, he is a great fluid dynamist, right. You are aware about Wankerman streets, where these vortex streets will be shaded downstream of the flow over a cylinder or any body, right. So, you might be aware, if you are not aware, just look at he gave the idea of transonic flow, that is the flow when it is between 0.8 to 1.2, in this regime it is called as the transonic flow. Question is, what really happens in this subsonic flow, and what happens in transonic flow, which we are going to see. And beside this, like when the flow is between the Mach number of 1.2 and 5 or less than 5, we call it as a supersonic flow. And when Mach number greater than 5, we call it as a hypersonic flow. Now, what is the difference between the supersonic and hypersonic? Similarly, transonic and supersonic, and subsonic and transonic, these we need to look at, because it will be helpful for us to appreciate the flow in general. Of course, we will be mostly dealing with the subsonic flow and supersonic flow in our analysis, and hypersonic we will not be really looking at it during our what you call this course, or discussion on this course. And question is, what is the difference, when we can call it as a flow to be subsonic? For that, let us consider a flow over an aerofoil. This is basically a slender body, and if some Mach number which is coming, which is less than 0.8, that means it is subsonic according to this regime, right. Now, what will happen if the flow is uniform velocity? Here you can see this arrow they are showing, it is uniform velocities, and if it will move in this way, giving a straight something very smooth streamline around this an aerofoil, right. What it indicates here? It will be subsonic. If it is subsonic throughout this region, then we call it as a subsonic flow, right. But I am having a doubt, why these streamlines are is like this. If flow is coming, right, for example, if flow is coming over here, something like this uniform flow, let us say in a wind tunnel kind of things, because uniform flow in nature is difficult to get, right. So, and then what I will do? I will put a body like a slender body or aerodynamic or aerofoil, right. If I do that, what will happen? The fluid will be moving. If I take this is coming over here and it will be impinging, and then there might be another one, I can look, it goes this way. Why does it go? Is it a intelligent like us, that fluid element? It will take a path. And how does it know that there is a body which is existing? For example, I know, like just now I was coming to take your class in a cycle. I found that in a police post, one young person was just going in the other way around, that is a round circle. He just went in the just cross that, take a shortcut route. He is intelligent enough, but he is not knowing that if he will go, he will meet an accident, right. But whereas, if you look at the fluid flows, if it is coming, it changes its path or the stream, these are basically streamlines or path, and move. That means, it is smart enough to say that yes, there is a body, I need to go in such a way that I won't bump into it. For example, if it goes this way, for example, if I say this is fluid is going here, directly hitting the body, you will get hurt, am I right? Is it so? That means, the fluid element is intelligent like human being, whereas, when I see our traffic and other things, we are not intelligent enough, we just get bumped into it, right. We do quarrel, we bumped into the people, right. That means, fluid element is smarter than us or intelligent than us, am I right? Then how does it do? There is no policeman to say that, look, go follow this traffic rule, or go this way, there will be problem, you know. Is there anything nature has given? No, na? Are you sure? It is, nature has given. That means, if there is a body here, right, and if the fluid is there, then it will be coming, of course, some fluid will be coming in the beginning. Suppose there is a fluid and I put a body, then it will give a sound wave and it will be moving with the speed of sound, right, and it will make the aware the fluid element to say, look, there is a body, you should take movement or change your path properly, otherwise you will hit on it. Are you getting my point? It is a very important point I am talking about. Therefore, the speed of sound is very important when you talk about Mach number, right. I could have put any other ratio. So, therefore, the Mach number plays a very important role to define or to divide the flow regime, whether it is compressible or incompressible, that we will learn as we go along. That is one thing. And other thing is that if the fluid element is moving here, so then what is happening to these streamlines? These streamlines are coming, but if you look at, there is a here there is a curvature of this body. If it is there, the whatever in figure these streamlines are drawn, is it right? For example, if I put a line here, this is my boundary, you know, then what will happen? If I take this cross sectional area, but simple argument I will say, and if I take here, what will happen? There is a decrease in area, right. Decrease in area, what will happen? You know from your previous learning, right. There will be acceleration. If there is acceleration of the flow, what will happen to streamline? It will not only deviate, but it will be crowded. It will be coming through, you know, closer, coming closer to that. I would suggest that you please read something about the streamline, stream tubes, you know, if it is a circular one, you know, what we will be dealing with, our propulsive devices, right. And this mass, because mass has to be, same mass has to move into. So, whatever the mass is flowing in this region, I have taken half of that, then same mass has to be moved into, right, in the same smaller area. Therefore, there will be decrease in velocity and the streamline will be coming closer to each other. But however, it is not drawn here, and if it is drawn, then or it is, that means the fluid velocity will be here more than the what is the free stream velocity at this point. Are you getting my point? So, therefore, it is very important. Then there will be increase in the fluid flow here. and as I told you that there will be also deceleration here in this region, there will be change in the Mach number. That means, local Mach number in this region will be changing. Am I right? If this is 0.8, will it be 0.8 throughout? It will be somewhere higher, somewhere lower than the 0.8 if I take, or if it is 0.5, then it will be different, right. That means, this region local Mach number of the fluid which is moving around it will be different, right. Now, if I increase my free stream Mach number to in the range of 0.8 to 1.2, what happens? For example, let us say my Mach number is around 0.9, that means, here it is 0.9, this is the free stream, I can write down this is 0.9, let us say, right, and fluid will be moving, there will be acceleration of the flow also, but it will be less than 1, and there is a regime where it is greater than 1, right. And if it is greater than 1, there will be a shock wave which will be discussing about this. Basically, there will be discontinuities in the flow properties, and discontinuities means what? It will not be the streamlined, will not be that smooth. If you macroscopically look at why shock is being formed, that we will see whenever we are discussing, right. And therefore, at the downstream of this, there will be Mach number will be less than 1. Keep in mind that I have shown only one shock wave on the upper portion of the stream, what you call aerofoil. What happens to the lower one? Will it not be there? In this figure, it is not there, right. Will it be there or not? There will not be, is not it? Am I right?
For symmetrical airfoil, it will be there.
But non-symmetric, it will not be there.
Positive angle of attack, it won't be there.
Angle of attack, that will be dependent on, and here we are assuming the flow is not separated. If flow is separated, then these streamlines whatever I have shown here would hold good, depending on whether where it is separated, all streamlines has to be changing, right. So, therefore, we are not considering what you are talking about, we are considering whether in this case flow is not separated. That means, angle of attack is not small, and there is no angle of attack here. You can look at it. This figure does not show that it is an angle of attack. It is a just angle of attack is 0 in this case. So, therefore, what will be? Whether the shock wave will be there, this region or not. If it is there, there will be. If it is there, then where it will be located? Will it be located exactly symmetric in this region, or it will be here, or it will be there? It is quite difficult to say, but however, one can guess that it will be little downstream because of this region. You can look at this surface, right. There will be when the Mach number will be greater than 1, will be attaining little bit down, right, because if you look at this surface and this one, you can see that. So, therefore, you please think about it and then have a feel for it. This is very important. And now, let us look at a flow. Here we have considered the Mach number range of the flow between the 0.8 to the 1, right. However, the transsonic flow, it is one region, that means, we are considering something 0.8 to sonic condition. You can ask me a question, why you are so particular about 0.8? Is it something so sacrosanct or magical number that it will be the same for all the time, or is there any basis? Is it that question coming to your mind or not? Because it is written in book, that is why we will have to take, am I right? There is nothing sacrosanct about it, it is just a mere thumb rule which is being done. It may be different when you conduct experiment. Suppose in case of what you call streamlined body, if I take a blob body, naturally this numbers what is given here like 0.8, 1.2, 5, need not to be the same. It will be generally, for example, when you go for this subsonic flow regime, it will be much lower than 0.8 when you talk about a flow over blob body, or some people call it as a blunt body. Okay. So, please you should develop a feel for it. Do not just remember the number, but you need to remember the number, but you should know what is the limitation. So, coming back to this, that then we need to understand what happens when the flow is between the 1 to 1.2, that is the transonic regime. What will happen if the free stream here is not really, it is greater than 1. What will happen? There will be shock. Where there will be shock? It will be leading edge, nearby leading edge, or it is away from the leading edge, or it is somewhere downstream of the leading edge. Where it will be? It will be before the leading edge, away from the leading edge towards the flow or the mainstream, upstream rather. That means, my shock will be like this, and this is considered as a bow shock, because it is like a bow, shape of the bow, right. And then when the flow is, let us say, Mach number which is greater than 1, then the downstream of this bow shock Mach number will be less than 1, right. Why it is so, we will see maybe when we will discuss about the shock. And then after that it became accelerated, and in this region the flow will be what you call supersonic. M is greater than 1, right. Mach number is greater than 1. And then there will be also a shock which will be here at the trailing edge, right. Both the upper portion and the lower portion, and it looks like what? Can anybody tell me? These two shocks looks like what? Have you never observed? What? No, this is shock, it is not expansion wave. But I am asking you, what is the shape you can have? Have you never seen a fish? Did you look at the fish shape? Is it not like an aerodynamic body or aerofoil? I mean, similar to that, right. It is having a tail, right. So, this shock we call it as a shock. See, when you look at nature, you should have a good observation power and try to relate what you learn and what they are having, right. If you look at most of the science, whatever we are using has come from the nature. So, nature is a great teacher to us. We must observe the nature as closely as possible. As I always say that we need to learn how to live with the nature, not live against the nature, because he is the our mother, right, sustains our all activities without any grudge in mind. This feeling is very important to when you are doing the science, technology or life, any other thing. So, therefore, we need to learn, this is known as fish tail shock, right. Of course, there is a little complexities here involved, we will not discuss at this moment, but however, some of you are interested, you can look at it. And keep in mind that in transonic flow, we get the flow subsonic, supersonic and combination, which is quite difficult to solve mathematically as such. And you will see that here also in this regime, the Mach number less than 1, Mach number greater than 1, we say that it is basically supersonic flow, subsonic flow, and therefore, we call supersonic subsonic combination is known as the transonic flow, right. So, if I will increase this Mach number beyond 1.2, what will happen? If I use this here in this what you call an aerofoil or a slender body, then the shock will be similar to your bow shock, right. And what will happen to the shock strength? It will be much higher as the Mach number goes, it increases. What do you mean by shock strength? We will look at it later on, but generally people use a wedge, in this case it is wedge or a sharp nose, where it which the shocks are being attached, and this shocks is attached and makes an angle. Therefore, we call it as an oblique shock, which we will be discussing little later on, how to handle the oblique shock, how to analyze oblique shock, and how we can use later on. We will see, particularly in case of supersonic air intake, we need to use this relationship for the oblique shocks and other things, right. And how we can design, how we can avoid the pressure losses and other things. If you look at what is happening here, Mach number greater than 1.2, I have shown any number between the 1.2 to the 5, you can see that fluid is going over here, and across the shock it is taking a turn, right. If you look at these streamlines, if you look at this streamline, lower one, what it indicates? It indicates it is a curved one, right. That means, this is a wedge or it is a cone, right. You think about it, we will come to that later on. So, therefore, if I am increasing this Mach number, what happens to the shock location? I am having one question to ask you, and there is another question, if this angle, this cone or wedge, whatever you call, let us say this is angle theta, if it is increasing, what will happen to the shock position? Will it come closer to the surface of this, or will go away? It will go away. Of course, that depends upon several conditions, like how far it is and what is the Mach number. Then it can be a bow shock if it will go certain limit values, which all those things we will be discussing when we are discussing about oblique shock and its relationship and how it behaves. Now, if this Mach number goes beyond the 5 is a number, and then what happens? The shock, this is the shock, right, will be coming closer to the this surface of the wedge or a cone, whatever you call, right. And then what happens there? What will happen? The temperature across this shock will be much higher, right. That is one important aspect. Beside this, as it is closer to the solid surface, it will be interacting with the boundary layer, and if the Mach number is more than 5, the temperature attained by in this boundary layer and shock the region, there will be boundary layer here, right. In this region, shock will be interacting. So, that right, this is your basically boundary layer, and it will be closer to that, and the thickness of the shock will be also very thin, or it is reduced drastically, and the gradient will be very high, temperature will be very high. As a result, ionization will be taking place and chemical reaction will be taking place. There will be quite complex in nature, right. And as a result, this has to be burned, right. And we need this thing whenever we are talking about the space vehicles re-entry. For example, ICBM, intercontinental ballistic missiles, or the Apollo lunar vehicle, which is when it is returning, right. That is at that time when you design, you need to take care what will be the effect of that on the body, so that it will not melted out due to the temperature, and it is quite difficult to handle. Also, this is the chemically reacting flows we need to consider. And like in case of Apollo lunar vehicle, while returning, what could be the Mach number they might be experiencing? It will be quite very high. What will be order? It will be around 36 kind of thing. ICBM, like intercontinental ballistic missile will be experiencing around 25, right. When I am saying, you do not go about exact number, but it is the range what we are talking about. Number, order is more important, or the kind of things. That means, like what will be that is quite complex things, and we will not be discussing about it, except when you are talking, sometimes we will be just mentioning about it. So, this is the flow regime which you must understand, and we will be revisiting and rather in detail about oblique shock, and there will be a normal shock here in this some region that we will talk about, and how to handle maybe expansion shock, expansions and other things. So, let us look at adiabatic steady one dimensional flow and apply some of the equations for that, and let us consider a nozzle, like let us say the station 1 is here, and we are saying this station 2, and flow is coming in this region, right, and flow is leaving at certain velocity. If you look at this itself, it shows it is the vector source is a higher velocity. Now, I want to analyze this thing, and as the name it indicates, this is the adiabatic flow. Therefore, there will not be any heat interactions, or heat is not going out, and steady. For that, we can consider it as a what you call as a steady one dimensional flow, right. And for the analyzing, we can take a control volume. So, control volume as usual, it will be adhering to the surface of this nozzle and also inlet. If you look at this is the fixed boundary, this is the imaginary boundary, right. And then we will have to look at this what you call apply this first law of thermodynamics for control volume. And what are the condition we will be looking at? We will be looking at that the adiabatic Q will be 0, that means this no 0, I am like Q or small q, Q is the specific heat interaction, and shaft work there is no shaft work as such. But can I consider this as a one dimensional flow? Is it possible, or it will be two dimensional flow, or it will be three dimensional flow? It will be two dimensional. Is it so? For example, if I take a pipe flow simply in a constant area, flow is taking place here, right, and I can say this is my z direction and this is my r direction. Of course, this will be my theta direction, right. And similarly, I will take another one, let us say my z direction, r direction, and this is my O and theta direction, right. In this case, if I look at flow properties, right, okay, and I will assume there is no boundary layer on the surface, that is also important one, or I will assume it is a fully developed flow, right, means flow is already developed here, there is no change, that means there is another portion which I have not drawn. Then what will be the properties? Properties, let us say pressure at each point will be function of z, rho is a function of z, similarly temperature is a function of z, and what about area? In this case area is a function of z or not? It is not a function of z, it is constant, right. It is constant, area is constant, cross sectional area is constant, right. But in this case what I will be? In reality this flow will be not one dimensional, this I can call it as a one dimensional flow. Can I call this flow as a one dimensional? If flow is taking place this way, can I call? I cannot. In principle it will be three dimensional, right. But if I say that theta, if I draw this and if I take this as a O, like any theta direction, any cross section theta, if I take d theta, kind of things, it will be same, right. So, therefore, this symmetric is there and everywhere flow is same, then I can say it is two dimensional now, right. But if I will assume this is symmetric in the theta direction, therefore, I can call it as a two dimensional, one is your z direction, other is your r direction. But if I will say this area which is changing, right, because cross sectional area is changing along with the z, but if the change is very very small, if I take an element over here, keep in mind this is a circular and this is rate at which it is change is taking place is very very small, then I can assume to be quasi one dimensional, right. That is P is function of z, similarly T is function of z and all other properties, then we call it as a quasi one dimensional flow, right. Please, this is a very important concept you must understand. Here the rate at which along the z direction area is decreasing is very very small, such that the property is not changing if you take a small element like this. Okay. This is my element, you can say dz in z direction, however, you can say in area wise it will be dA, area change, right. If I take this, this will be basically like this kind of things, cross section. So, this change in area in comparison to this, it will be very very small. So, this is a very important concept, you must appreciate this, and here we are doing the similar thing as well. However, it is not very obvious from the equation, we will be looking at in little detail later on. Here I am considering this as a equations of first law of thermodynamics for control volume, which state that H 1 plus V 1 square divided by 2 is equal to S 2 plus V 2 square divided by 2. Now, this equation I have just written, do you agree with this? How it has come? From where it has come? H 1 plus V 1 square divided by 2 is equal to S 2 plus V 2 square divided by 2. From where it has come? Energy equation. So, if I want to write down energy equation, what it would be? I must know that, right. Then I will have to make this what you call make the assumptions, whatever that Q is equal to 0, shaft work is 0, then I will have to do that, and there is no gravitational or the potential energy change, right. I want to write down for you, let me do that. So, if you look at this equation, thermodynamics for a control volume, and keep in mind that we are considering what you call one dimensional flow. Okay. That is very important. Generally, flow is uniform across this a cross section what we are considering. So, I can write down dE by dt is equal to is plus m dot 2 if I take a station 2, and it will be H 2 plus V 2 square 2 plus G Z 2 minus M 1 H 1 plus V 1 square by 2 plus G Z 1 is equal to that minus W sapped, right. Now, in this case what is happening? We are not considering these potential energy terms, and this is a steady flow, right, and there is adiabatic flow, this is sapped work. Then I will get S 2 is plus V 2 square 2 is equal to H 1 plus V 1 square by 2, provided what? Provided provided m dot 1 is equal to m dot 2. Is it true? Because if I apply the continuity equation, one dimensional continuity equation, what it would be? dm by dt is equal to m dot 1 minus m dot 2. This is 0 because of steady flow. So, therefore, m dot is equal to m 1, and then we arrive at this, and this is the energy equation for what you call the one dimensional flow under steady state condition with of course, no sapped work and adiabatic in nature. So, if I convert this equation in terms of what you call temperature, what I will do? I can write down in place of enthalpy, I can write down C p T 1 plus V 1 square divided by 2 is equal to C p T 2 plus V 2 square divided by 2. How could I write this? Under what condition I can do this? Can anybody tell me? We are assuming as an ideal gas, right. What kind of ideal gas it is? It will be calorically perfect gas, because the Cp is a function of temperature, Cp is also a function of kind of fluid. If it is oxygen, it will be different. If it is helium, it will be different, right. If it is carbon dioxide, it is different. What are the difference between three examples I have given? One is monomolecule, dimolecules and trimolecular structures, right, atomic, right. So, therefore, its Cp will be different, and here we are assuming that specific heat or the Cp is also a function of temperature. In this case, we are assuming that Cp is not changing with temperature. When it will be valid? If the change in temperature is not much, but in case of combustion, we cannot really do effort to do that. Of course, we will be doing, but with making a lot of error in that, right. So, therefore, you keep in mind that we could do this conversion for the calorifically perfect gas, right. Now, what we will do? We will put this in place of Cp, we will express in terms of the gas constant, that is specific gas constant, that is R. What we are saying, what we will be doing, will be in place of Cp, I will be using Cp is equal to gamma R divided by gamma minus 1, and keep in mind that ideal gas equation is equal to P rho R T. So, if I write down in place of Cp as C gamma R gamma minus 1, it is here, and in place of R and T, if you look at this T 1 R T 1, it will be P 1 divided by R 1 from this equation of state. For an ideal gas, you can write down P 1 divided by R 1. Of course, V 1 square divided by 2 remains same, and similar thing for the right hand side. Can we recognize this equation? What kind of equation it is? All of you are exposed to the fluid mechanics earlier, and even what kind of equation this is? Can anybody tell me what it says? It says basically ratio of pressure and density, right. This is the velocity, particularly you can think of in terms of kinetic energy, right. And what is this? Can you say anything about this term? I mean, I am expecting an answer. P by rho 1, P 1 by divided by rho 1, what it indicates physically? What do you mean? Speed of what? Speed of sound? Where speed of sound comes into picture here, right. So, if you look at this is, of course, what he has told, it is similar to that, but however, it is different. Physically, if you look at, it will be like making a flow. What will make the flow to happen? It is the pressure, if I look at in that terms, right. So, but this is applied basically, and if you look at, can I call it as a Bernoulli's equation, right, and generally people call it as a Bernoulli's equation for compressible flow, right. And but however, in some of people dispute, they say that like Bernoulli's equation won't be there for cannot be applied for compressible flow, right. But however, it will be convenient because it is similar to that. Let us see that whether we can derive a Bernoulli's equation considering the flow to be isentropic and steady one dimensional. When I say that isentropic, it is basically change in entropy is equal to 0, right. If change in entropy is equal to 0, then what will happen to this first Gibbs law or expression? Sometimes people call it as a Gibbs expression, that is TdS is equal to dH minus VdP. I think I had discussed in the last lecture, this is a combination of first law of thermodynamics and second law of thermodynamics together, we will get this expression. Some of you might have looked at and see that how it is derived and what is its implication. So, if it is an isentropic flow, then I can make it is 0. So, what it indicates? This expression equation 6, it indicates that dH is equal to VdP, and then if I use this equation 6 in equation 5, which is nothing but what? Energy equation for adiabatic flow, but it is not isentropic, right. Okay. Then what I will get? I will get an expression is equal to P 1 plus half rho 1 V 1 square divided by 2 is equal to P 2 plus rho 2 V 2 square divided by 2, which is very familiar to with you, right. What is this equation? This is your Bernoulli's equation. What is the validity of this equation? and what it indicates to you. If you look at these terms, this basically says what? The first one is your pressure, that means this is the pressure work or the pressure, right. The work will be done on the fluid, so that it can flow. As a result, there will be kinetic energy, right, change in energy. That means what is saying, if pressure increases, what happens to the velocity? Decreases. But we know that in the pressure gradient is more, then velocity will be more. There is something contradictory, am I right? Then how will interpret this? But from this it says, if I take station 1 P1, I mean and the pressure P1, and then at the station same place at 1, it will be velocity is V1. If pressure is decreases here at the station 2 here, what happens to the velocity? Velocity will be higher, because the total is remaining constant. That means, total energy is remaining constant at between the station 1 and station 2. Am I right? Okay. Of course, there is another term which is there due to the elevation kind of things, which we have not considered, what we call it as a potential energy. That means, what it indicates? It indicates that the energy equation, that is the equation 5, is same as that of the equation 5b, which comes from what? Momentum equation, right. You can derive that, and this is valid for what? Steady incompressible equation 5b, okay. And then isentropic flow, and whether rotational or irrotational. Why? I did not talk about it, because if it is rotational, then entropy has to be changing, particularly when near the boundary layer. So, and also it will be dissipated kind of thing. So, therefore, it is valid for one dimensional steady irrotational flow, and therefore, we call it flow along a streamline, right, where mass will be remaining constant. That means, if you take a stream tube, that mass at any section is remaining constant. Therefore, continuity is valid. Okay. So, therefore, like one has to consider that along a streamline it will be valid. Okay. So, and I have already told you that rho v square is the dynamic pressure and P is the static pressure, right. What do you mean by static pressure? Can anybody tell me what do you mean by static pressure? Is there okay, fine, go ahead.
Is it exerted by a fluid molecule when it is isentrophically brought to rest?
Brought to the rest, right. How I will get it? If I say that I want to measure, how can I measure it? Is it I will make the fluid to come to the rest isentropically? Is it possible I can do that? That means what it is? Can you people think about? You imagine that you are hopping over a fluid element, or maybe a sensor which is hopping on a fluid element. That fluid element is moving at certain velocity. That means, it is right. If there is a fluid element and I am having a tiny center, of course, it is quite difficult, imagine that, and then it will be experiencing certain pressure due to what? As it is moving, right, a element will be having certain velocity. As it moves different places, it may be experiencing different velocity, that is a different thing, but then what it will be experiencing? It will be experiencing a pressure or a force. The force is due to the molecular interaction. That means, molecules will be coming and bombarding each other. That means, that pressure which will be felt due to the change in the what you call momentum change, that you will get the pressure, we call it a static pressure. So, for an ideal gas, equation 6 becomes, I can write down ds will Cp dt by T minus V dP by T is equal to gamma r divided by gamma minus 1 dt by T, right, and minus r dP by P is equal to 0. Are you getting this? This what we are getting? We are basically equation 6 I am taking and looking applying this, changing these Cp values and putting this equation of state, and we are getting P is equal to rho R T. If I apply this ideal gas law, then I can get into V by T R by P, right. And then if I say gamma is basically ratio of Cp by Cv, then I will get this expression P 2 by P 1 is equal to T 2 by T 1 gamma minus 1. Keep in mind that this is not visible, but look at it, right. That means, this is the expression for an isentropic flow relating the pressure and temperature. With this I will stop over it, but let me ask a question before stopping over. Why we need to look at this isentropic flow equations or expression, which is being used profusely, and we will be using it, left and right in our analysis. Why it is so, we will discuss, we should think about it. So, I will stop over here. Any questions? Okay, thank you very much.